Hello everybody, today I'm going to explain how to solve an older USACO problem which was given in the 2018 February contest in the Silver Division, and its problem teleportation. Even though it's an older USACO problem and most of the USACO problems nowadays are harder than they used to be back in the day, this problem was actually quite difficult for its level at that time, and even to this day it's a problem which causes people to have more difficulties due to its unusual type. Because as you will see, there are certain observations that don't show up in many problems, and I will use this video as an opportunity to explain the ideas behind the problem as well as how to come up with them by yourself. Without further ado, let's begin. So in this problem, we are given n pairs of points, and for each pair of points, we know the starting position as well as the ending position. And Farmer John has a choice to make for each of the pairs of points. So he can either go from A to B in the usual way on the integer axis, or he can use a teleport, which will go from the first point to the first endpoint of the teleporter, which is x equals 0. Then you will teleport to the second endpoint, and then you will go to the second point, to your destination. But there is a catch here. While we know that the first teleporter is at position x equals 0, we don't know where the second teleporter is. And this is basically what we will have to do in this problem. To find the location for the second teleporter, such that the sum of distances will be minimum whenever we will place the teleporter. So minimum among all possible choices. Now, the first thing we need to do is to compute what would be the best option for a pair of points. So let's assume that we have xi and yi. And now, if we go from xi to yi, we will assume that xi is to the left of yi, but it doesn't matter that much. So if we are on a line axis, then we have xi here, yi here, and we can just go from xi to yi directly by using the absolute value between xi and yi. So this would be the first option. Now, the second option is to use the teleporter and hope that it will help us get to our final destination. So obviously we can go to 0. This is where the teleporter is, so 0. And we will have the second teleporter, which is at a point y. And in the second option, we have a different formula. The formula will basically be the distance between xi and 0, which is just the absolute value of xi, plus the absolute value of the difference between yi and y. So basically, we will have two terms in our formula, and for each of these pairs of points we are given, we need to decide which option is better. Now, obviously, we didn't fix y yet, so we need to think at how to do that. A way to solve the problem, which would be very slow, however, will be to try every single possible y, and for each of them try to find whichever option is better. However, there is a huge problem with this. The points can go between negative 10 to the 8 and 10 to the 8. So therefore, y can be somewhere between negative 10 to the 8 and 10 to the 8 as well. So we have to check around 2 times 10 to the 8 points, which would be a lot. And given that we also have up to 100,000 pairs of points to check, we would have a complexity for a brute force solution, which is n times 200 million. So this is way too much. So we will get TLE. Now, how to avoid the TLE? The main thing we need to consider is that no matter what we do, we will always have the first option. even if the teleporter is placed in the worst possible way. But if the distance from xi to the first teleporter plus this distance is small enough, then using the teleporter would be a good option. So therefore, what we can consider in this part of the solution is to try to identify for each pair of points the range of values where it will be better to use the teleport and the range of values where we will use the default option. And given that we know this expression, we can define the difference between this entire term and xi, and this will make us solve a first degree a linear equation. So just a very simple equation. So if we write a bit, and let's note this with a and not with a, maybe we can note it with let's say a p and this one with an r. We can say that the absolute value of y minus yi will be at most equal to p minus r. Obviously, absolute value is always positive. So if assuming that p minus r is greater or equal than 0, we will get to a relation which will be something like minus p minus r greater or equal than smaller or equal than y minus yi, smaller or equal than p minus r. So obviously given that we know where yi is, we can just add it up, and then we will get to have something like minus p plus r plus yi, smaller or equal than y, smaller or equal than p minus r plus yi. So basically, I just rewrote this equation, and now we got to a more simple relationship. However, when we think about what will be the actual distance for each of these points, we will observe something interesting, assuming this equation holds. So if we look at the chart of, let's say, f of x or f of y, more like f of y, then the minimum distance we will have every time we fix a teleporter point will look either like this. So we have here the default distance, then it will start going down, then up again at the same rate, and then it will be just the same. So basically we will have a distance which goes down, then a distance which goes up. So this is obviously the case where we go with xi minus yi. And obviously here, as we get closer to the minimum point, which will be at yi, and then again the distance will get back up. Now when we think about it, basically now we have two choices in our hands. So we want to find out where we get these better or worse answers. And now it will be a bit harder to model a function which goes down linearly unless we observe something quite cool about it. The answer for where it's optimal to place the teleporter is always going to be an integer. And because of this reason, we can now try to think at a way to measure the rate of decrease or the rate of increase, because basically if we have each of the integer points on this axis, basically the decrease will always be linear until it will stop, and then it will start increasing again. So I will try to draw them as symmetrically as possible. And now an idea we can think about is working around slopes. So we can think now at a way to measure where will a slope start, where will a slope decrease start, and it will start once we get to this point here. And then the slope will keep decreasing until we get to the minimum, which will be yi, and then it will keep increasing again until we get to this point. So now we can reduce it to, for each of the pairs of points, to 3 events. First, we have decrease. Then the decrease will no longer happen and we start increasing. And then it will become again flat. We can also consider that it was originally flat. So it would be more like 4 events, but this first event is actually at the beginning of our interval. So not very relevant for what we need to do. Now, because we have these 4 events, we can modulate them as queries where we would have either a negative value or a positive value. Obviously, we would start here with having a negative value, a -1. And now in order to adjust for this negative value and to also have positives, we will have to actually make up for the negative value and also increase it. So it will be something like +2, because we want to also model the increase that will happen. And then here, in order to get everything back on a neutral path, we will decrease 1. So now that we did this, we only have 1 step left until we are done with solving the problem. We can sort these events, and as we go through the events, you will observe that I will keep track of a prefix sum of the slopes, as well as a prefix sum of the decreases we will get as a result. Because if we have, let's say, a -1 starting from here, by the time we will arrive here, the total amount of negative changes can be -5, -10, or whatever. It can be very big. So we need to keep track of that as well. And basically, because the points are very big, we will have to use maps to store these events. And after we are done with it, all we will have to do is to check only the relevant points, which will be the given 2 times n points. Each pair has both points as relevant points, the point 0, as well as whenever these changes in slope happen. And basically, if we consider the idea, it's about thinking at each interval as its separate equation, doing the math to get to the interval where teleporters work well, and then using difference arrays and maps to store the computations. And now let me show you the code. So as you can see, I read each of the pairs, and I added here the relevant points. I want to add everything, even the points which are not necessarily places where the slope changes, just to check them all. Here is the usual distance if we don't use teleporters, and I keep it in a total distance because basically I want to find something where the sum of decreases is as high as possible so that I would get to an optimum position. And here we have a decrease in distance when we get to where the slope starts going down. Then here, after we got past the minimum, we will add 2 to make up for the decrease and to also start increasing, and then the distance becomes flat. Because we are using a map, the points will be sorted, so all we will have to do is to compute the prefix sums in the style we see with difference arrays. And this can be done by just keeping track of the previous point and making sure we are not at the first point to avoid any extra calculations. And then we will compute the minimum answer over all ways to choose the relevant point. And as you can see, this code is quite simple and way less complicated than the editorial solution. And even though a lot of the details from the solution I just presented are quite similar to the details in the editorial solution, the way they came up with all of these cases makes it harder to understand from my experience, and this is why I wanted to record this video. And also it's a very good problem for understanding how to use difference arrays, how to combine them with some math, as well as when it comes to sorting and searching. And if you enjoyed watching this video, please like the video, subscribe to my channel, and show this video to everyone who is interested, be it in USACO, competitive programming, or just learning more about algorithms, data structures, and problem solving. Also, check out the links in the description for more ways to interact with me, as well as for various opportunities to get better opportunities in general, be it for work or for other AI projects. As usual, thanks for watching, and I will see you next time. Cheers.